Welcome back. We have Nati Seiberg from IAS, who will tell us about anomalous continuous translations.
Thank you. It's a pleasure to be back at Oxford, and thank you organizers for putting together this wonderful conference and for inviting me to speak here. My topic is anomalous continuous translations, and I'll describe work that appeared recently in this paper. In this paper, I also commented on the relation between the lattice and the continuum, but in this talk today, because it's only half an hour, I'll talk only about the continuum. There will be nothing about the lattice in this talk. The other thing I would like to clarify before I start is the word anomaly here. You have heard the various speakers use the phrase anomaly in this conference, and there's a fine distinction between 't Hooft anomalies and ABJ, or Adler-Bell-Jaquiev anomalies. The original anomalies were due to Adler and Bell and Jaquiev. The more sophisticated version is the 't Hooft anomaly, but logically they kind of come first. All the anomalies I will be talking about today are Adler-Bell-Jaquiev anomalies, so I'll just give a definition. This is a situation where we have a classical system that has a symmetry, but a quantum theory, for one reason or another, does not have that symmetry. So that's unlike the 't Hooft anomaly, which does not signal any disease in the theory, no symmetry is ruined, everything is fine, except that the symmetry has to be handled with more care. Here, the symmetry is just gone in the quantum theory. So after we got that thing out of the way, I would like to start with telling you first, very briefly, which theories are we talking about. So I'll characterize them in a general way. I think the story can be generalized even further. This is a rather generic phenomenon, which for some reason is not quite there in the literature. So the models I'll be discussing are continuum field theories. For concreteness, I limit myself to work on a d-dimensional space. D will be the number of space dimensions. And I'll take space to be a d-dimensional torus, flat torus. And I'll be interested only in models that have a d-2 form U1 global symmetry. And I had parenthetically that for this purpose, we can even work in 1+1 dimensions, and this would be a -1 form symmetry. That's actually completely straightforward to include also that case. So these are the models that we discuss, and that sounds like a mouthful, but there are very special cases that are easy to relate to. First, any U1 gauge theory in the continuum has a d-2 form magnetic symmetry. And so it already fits in this. So if we have a U1 gauge theory in d dimensions, any d, 1, 2, 5, we can put it on a torus, and it satisfies these requirements. And then the phenomena that I will be talking about are when the model has constant charge density, which means that I add to the Lagrangian a term proportional to A sub t. So that's one class of models. The other class of models, which are deeply related to the first class, is certain nonlinear sigma model, where the target space has some properties that I will spell out later. And the Lagrangian includes various terms with one-time derivative. So a characteristic example is a ferromagnet. The ferromagnet has such a term in the kinetic term, a first-order time derivative in the kinetic term, and then in the dot, 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 both here and here, we can have all sorts of terms with second derivatives, more matter fields, other interactions, etc. I'll describe what this means geometrically in more detail later. So all these models have the following peculiar features. First of all, the classical Lagrangian is not well defined. In the first example, it was not gauge invariant. In the second example, it's not globally well defined in the target space. However, if we look at the equations of motion are the variation of the Lagrangian, they are globally well defined and gauge invariant. So a classical physicist who studies these models would say there's nothing peculiar about these models. The equations of motion are fine, the Lagrangians are bad, but this is Lagrange's problem, this is not Newton's problem. Newton was only interested in the differential equation, not in the Lagrangian. Second, everything looks translation invariant. I wrote down the Lagrangians. There's no explicit x dependence, and the equations of motion are positionally at translation invariance, etc. So all these models are well defined and have continuous translation symmetry. As we move to the quantum theory, we need to define the Lagrangian more carefully. In fact, the Lagrangian and even the action do not need to be well defined. Only the exponential of the action needs to be well defined. But this now has to be well defined as opposed to the classical theory where only the classical equations of motion have to be well defined. So how are we going to define that? Requirement number one, we should make sure that in the classical limit we recover what we had before. So we might need to work a little bit, add terms, quantize coefficients, etc., to make sure that the quantum theory is well defined. And in the process of doing that, we might find the need to introduce additional data. If you find that too abstract, think of the theta parameter. The theta parameter does not appear in classical physics. It does appear in the quantum theory. The theta parameter multiplies the total derivative, and as such, it does not affect the equations of motion. So the quantum observer sees dependence on theta, but the classical observer doesn't see dependence on theta. In our case, the additional parameter that is needed breaks explicitly the continuous space translation. I got to say that first I realized that I was quite surprised because the system appears to be manifestly translation invariant, but in fact it's not. You have to make a choice of where the origin is. Once you made a choice of the origin, everything is well defined. Furthermore, as we will see, the continuous translation is broken, but it's broken to a discrete translation subgroup, and that discrete translation subgroup is further extended by the D-2 form global symmetry charge. They're very strange properties, but it turns out that many of the results that I will present, if not all of them, have already appeared in the literature in one form or another. They appear together with some controversy about the meaning of the results. Is it really correct? Is it because we didn't define the operators carefully? Is this a subtlety in how you regularize the theory? Is it because we put it on the lattice or not? There was a lot of confusion about it, although many of the elements are there correctly. The point of this talk would be to give a unified treatment to all of them and also presenting new special cases. And I will present it as an ABJ anomaly in translation. So that's the summary of the talk. And before I start really going to work, I want to set up the notation. Space will always be a flat d-dimensional torus parameterized by xi. The total volume will be the product of the LIs. Lorentzian time will always be t, Euclidean time will always be tau, and the index mu runs over space-time, either Euclidean or Lorentzian. So I'll always follow this notation, and then I will not explain it. Yes, already a question.
When you consider U1 gauge theory, you always consider compact U1 gauge theory.
That's compact U1. For me, U1 is a compact group. I know I differ from most condensed matter physicists who like to discuss non-compact U1. There is no such thing as non-compact. U1 is compact, R is non-compact. The group is U1. Now, this is totally unrelated, once we are at it, this is totally unrelated to the existence of charges. Dynamical charges might not even be present. The gauge group determines which bundles I study. That's independent of which charges I have. And U1 was compact and will remain. I'll also have CPN later, and I'll say my CPN is compact. This is because many people like to discuss non-compact CP1. Yeah. So once we got the terminology straight, the first example I'll study will be a U1 gauge theory with constant electric charge. As far as I know, this problem was first studied in '79 with some very confusing interpretation. Max Metlitsky wrote a beautiful paper in '07 with surprisingly few references, where he got a much better picture of what's going on, and there's a little bit of a follow-up. So what are we going to do? This is the Lagrangian. We take standard U1 gauge theory and add to the Lagrangian the term rho times AT. We look at the equations of motion, we differentiate with respect to AT. That what we get is Gauss' law, but now because of this term, Gauss' law has a number rho on the right-hand side, describing constant charge density, and hence the notation rho. So the classical equations of motion are perfectly meaningful and translation invariant, and they state that there is constant charge density rho. What happens in the quantum theory? In the quantum theory with h bar equals 1, this rho has to be quantized. It should be an integer divided by the total volume. One way to see that is that K is the total charge of the system. It should better be quantized. See, for example, Chaugan's question. So the total charge of the system has to be quantized. One way to see that is to put the system on the Euclidean time circle and perform large gauge transformations that wind around the circle, and they quantize this quantity. A statement that appears often in the literature is that once rho has that coefficient, so what we have here is quantized in this form, the theory is gauge invariant, because after all, what can go wrong? I've already established invariance under large gauge transformation that wind around time, so this thing looks perfectly consistent, and in particular, it's manifestly translation invariant. There's no explicit dependence of X. As I wrote here in green, that's actually not true. This theory, as stated, is not translation invariant. It's translation invariant classically, but not quantum mechanically. Now, how should we define the theory quantum mechanically? The proper way to define it is to go to your friend, the mathematician, and learn a little bit about differential cohomology, and they will tell you exactly how to define this object. This is a little bit above my pay grade, so I'll present a lowbrow version of the same story. That would be my first derivation. My second derivation will not use even the details that I will have. I'll have a trick where I will use a fact that all of you are familiar with, which actually can be justified using the differential cohomology or my detailed analysis. But given that you all know the fact, I will just use this thing, that you know the fact, and then derive the answer in 2 lines. So I'll first go the hard way. So we need to define the theory. I put it on Euclidean space-time on a torus, and I covered the torus with patches and transition functions between them. I'm sure everybody here knows what it is. So I'm taking the transition functions to be along d-dimensional tori. So I pick a point x star. This is my choice of local trivialization. And as I cross this point, the gauge field is shifted by a derivative of the transition function. And then I have to define various gauge invariant observables. So the first one is the holonomy around Euclidean time. So the first term is obvious, we just integrate the gauge field. But if we have transition function in the time direction, in the Euclidean time direction, then we have to put a contribution due to the transition function there. This is completely standard. The holonomy, if we write it explicitly in terms of patches and transition functions, this is the holonomy. Now, the object that we are interested in is this, the integral of a tau, with the coefficient properly quantized. So the first thing we need to do is add this correction term that came from the holonomy. But what can we say about this object? Is it gauge invariant and meaningful? To do that, let me shift my choice of x star, where the transition functions are. If I shift x star, various transition functions move from where they are, and the action is shifted by a term proportional to the field strength. More mathematically, this is the first Chern class in the tau direction and the I direction. There's a 2 tori, and the action is shifted by that term. That's actually quite surprising because we took something that looks innocent, but now we see that despite appearance, it depends explicitly on the coordinate. Depends on the coordinate of the local trivialization that we chose. So that's what we saw. We saw dependence on this x star. And we can easily fix that by adding another term to the Lagrangian, a term proportional to the field strength with explicit x star dependence, so that as we shift x star, the contribution from here cancels from what we had in the leading order term. However, now we have dependence on the choice of origin. So regardless of how you look at it, the theory is not translation invariant. If you did not follow the details, don't worry, I will soon give another derivation of the same fact. The upshot of all that is that the Lagrangian and even the exponential of the action, regardless of how you define them, they are not translation invariant. They are shifted under translation by this term. That's not obvious from here. Notice that this has nothing to do with the measure in the functional integral. It does not depend on whether the functional integral is convergent or not, or how I regularize it and so forth. I just want to make the integrand in the functional integral well defined. That's my goal. So that's the result. But the first thing we notice is that a classical physicist, let's go back and have a sanity check. The classical physicist wouldn't care. This is a total derivative. And since this is a total derivative, if we're only interested in the equations of motion, this correction term is totally harmless. So that's the first fact. The second fact is that this object is quantized. So if we shift not by an arbitrary epsilon, by an epsilon which is 1 over k, k being the coefficient in the Lagrangian, 1 over k times the total length, this thing comes back to itself, so the theory is invariant under shifts of epsilon by this discrete amount. Now, as I said, these terms do not affect the classical equations of motion and therefore do not affect the classical theory. They do affect the quantum theory, but I emphasize they have nothing to do with the measure in the functional integral, divergences, and so forth. So that's what we learned, that the careful definition of the Lagrangian needs more data, and the data we had was that we had to add is a choice of origin in space. Mathematicians have all sorts of fancy ways to say that, but I will not go there. So the quantum theory does not have continuum translation symmetry. We do have discrete translation symmetry if we shift by 1 over k of the whole circle. And therefore, instead of having u1 to the d, d being the number of dimensions, we have zk to the d. So I interpret that as an ABJ-like anomaly in translation. In the ABJ anomaly that figured in some of the previous talks, there was a U1 symmetry, and it has an anomaly. It was a chiral anomaly. And sometimes, depending on the charges of fermions, the anomaly explicitly breaks the U1 chiral symmetry to a ZK subgroup. Here we see something very similar, but it's not in a chiral symmetry, it's in translation. So that's the only difference. And furthermore, if we look more carefully at the translation generator, we can see that these two translation generators in different directions do not commute with each other. In fact, they commute to the higher form charge, which is the magnetic flux in there. And since the magnetic flux is an operator in the theory, that's not a central extension of the translation symmetry, it's actually an operator extension. So the symmetry group is complete. The symmetry group of the quantum theory is first discrete rather than continuous, and even the discrete group is not zk to the d, but it's further extended by this operator. So take a breath, long breath, and say, this might seem too deep. Got into the nuts and bolts of how we define things with transition functions and this and that. Let me give you a quick way to do that, which immediately gives the answer. So one of my themes in physics over the many years I've been doing it is that wherever you see a parameter, think of it as a background field. And let it depend on time. Try to generalize the theory and view it as a representative of a larger class of theories where we vary the parameters. So how are we going to do it here? So the theory we discuss has a d-2 form symmetry, which is the magnetic symmetry. It's a topological symmetry, and whose current is the field strength, d little a. And if we have a symmetry, we've heard that from many speakers in this conference, if we have a global symmetry, the first thing to do is to couple it to a background charge, to background gauge field. So we need an appropriate gauge field, and what we do is take the current times the gauge field. That's the coupling. So writing it explicitly, this is the magnetic field of the dynamical U1 gauge field times times a background gauge field for this d-2 form symmetry. We've seen couplings like that in almost every talk in this conference. I think all of them. Now, this is a Chern-Simons term, and it has to be defined carefully. So instead of trying to define the term A sub t, so let's define this Chern-Simons term. And instead of defining Chern-Simons term, let's just take the standard definition in the literature. This is a BF theory, except that one of them is dynamical, the other is classical, so we need to define it carefully, and we copy the answers from the literature. And when we do it correctly, this term can be written in this form. Now, there's a peculiar fact about this Chern-Simons term. In this way of writing things, it looks like the answer is independent of the constant mode of little a. It does depend on the constant mode of big A, but it is independent of the constant mode of little a. In this way of writing it, it looks like it is independent of the constant mode of big A, but it does depend on the constant mode of little a. The correct answer is that it depends on both. One of them is more manifest in one presentation, the other dependence is more manifest in the other presentation. And the reason it depends on both is that when you define it carefully, you get dependence on the other parameter, which appears like it's not there. The way I described it before, it appears through dependence on what happens in the transition function. In any way, I'm going to take this theory, and I'm not even going to tell you how I'm going to define it, except that I'm going to define it the same way it was defined for all the other speakers here, who did not even bother to define it carefully because they took it to be well known. And I'm going to study the system in a particular background field, the background field of constant magnetic field to big A, not to be confused with the magnetic field of little a, which is the dynamical field. So I take A, the background field A, to be such that it's proportional to the volume form. It's a constant magnetic field. This is a particular background that I could study. In this case, the coupling that we have, if we write it in this form, is exactly the coupling we are interested in. So a way of writing our coupling with the term linear in A sub t, a way of writing it is by turning on background big A of this form, constant flux. So now, as I said before, it's known that despite appearance, this Chern-Simons term depends on the constant mode of big A. So a puzzle before was that we had something like this. I didn't even mention big A in the first presentation. There was also only something that depends on little a. There was no big A, but secretly there was a big A here that I didn't write, and the constant mode of it does affect the answer. And the dependence I got on the origin that I had to choose crept in through the zero mode of big A that I didn't write. In fact, if I integrate by parts, and I write this thing as d little a times big A, we know that in order to get such a big dA, which is constant, big A must have a term depending on x. Could be at least linear in x. So the background gauge field explicitly depends on x, even though the field strength is independent of x. We are familiar with that in the quantum theory, in magnetic fields. When we have magnetic fields, then if we have particles in a magnetic field, or we have in general a magnetic field, the magnetic field is constant, but the vector potential depends on x. So the fact that the symmetry is broken to the discrete symmetry, and this discrete symmetry is extended, that also follows. I'm not going to do it here in detail. So this discussion suggested an obvious generalization. Take any continuum field theory that has a d-2 form U1 global symmetry. So that means that we have a closed 2 form big J with integer periods. That's a statement that there is a d-2 form global symmetry. And in our U1 example, that was the field strength. Now we follow the same route we did before, except that I don't even have to mention that I have a U1 gauge theory. I couple it to the background field, and I specialize to a particular background field with constant field strength. Now A, and therefore J times A, are not translation invariant, but it's not manifest in it is manifest in this form, but not in the other. So they're not translation invariant, but if the current J, big J, is topological, i.e. dJ is true, is zero even off shell, then locally I can solve for phi and write the conserved current as d of something that is not globally well defined, but locally it can be defined locally. And then our coupling is a term linear in phi t. So whatever I said easily generalized to all these examples. So classically the system is translation invariant, but quantum mechanically the system is not well defined. And if you write it like that, the definition needs more care. So now I just copy the results from before. We use this background, and when the symmetry is topological, we have this phi t. Classically, it's translation invariant, but in the quantum theory, we break the translation symmetry. Let me specialize to a particular example, a nonlinear sigma model. So let the target be a non-trivial second cohomology with integer coefficients. So one of the generators denoted by big omega, and therefore we have a d-2 form symmetry. We have a d-2 form symmetry whose current is d phi. Phi is not globally well defined, but the current is. So here are some examples. If the target space is S2, that leads to a sigma model. If the target space is T2, it leads to a two-dimensional field theory. in 2 dimensions, and 1 plus 1 dimensions leads to a famous CFT. It can also be a Calabi-Yau manifold. The target space could be anything that has such cohomology. As ended the general discussion, I'm just turning the crank and do the same thing again. We have a current, and we can couple it to a background gauge field. J is locally d phi, so I can integrate by parts. I get a term linear in phi t. No background field, I don't have to think about them. It is first order in time derivatives. And now the translations are anomalous. Translations are broken to a discrete subgroup. And when the number of dimensions is larger or equal to, the algebra is extended. In the special case where the sigma model is a symplectic manifold, we have another simplification that happens. First of all, the various objects have names. Phi is known as the pullback of the Liouville potential to space-time. We have a map from space-time to a symplectic manifold. And phi, that appeared before J was d phi, so J is the pullback of the symplectic structure, and phi is the pullback of the Liouville potential. So first of all, it has names. We don't need to reinvent the wheel. And in that case, all the terms, this is a first order derivative in time, all the terms that are second order or higher derivatives in time are negligible at low energies, and therefore I can neglect them. This appears in various applications, particles in the lowest Landau level, in the O3 sigma model, and ferromagnets. So let me give this example in more detail, and then I'll finish. So let's start with an antiferromagnet. We have an antiferromagnet in any number of dimensions. At low energies in the continuum, it is described by the O3 sigma model. So this is something that people study in the first course in condensed matter physics. We have an antiferromagnet at low energies. The SO3 symmetry is spontaneously broken to U1, and we describe it by a nonlinear sigma model. Now, this sigma model is a d-2 form symmetry, known as symmetry associated with skyrmions. I think that's not in the first course in condensed matter physics, but maybe in the second. So they're skyrmions, and they are associated with this conserved current. And it follows the general rule that I said earlier about symplectic manifold. This is in the case of S2. So we couple it to a background gauge field, so it's the same thing again. We have a symmetry, we couple it to a background gauge field, we pick a particular background with constant field strength, and then the term we are interested in is this one. And this term is not globally well defined. It does not decay fast enough as z goes to infinity. And this term is known in the literature as the Berry term. There's nothing new about that. Some people refer to it as the Wezumino term. And it describes, at low energy, this system describes the continuum limit of a ferromagnet. So the way to move from an antiferromagnet to a ferromagnet is to add this term. That's known. I'm just giving it a new interpretation, that this term can be thought of as the response to a background gauge field for the skyrmion global symmetry of the system. The fact that this system breaks translation symmetry has already been noted by Haldane in '86, so this is really ancient. And there's been a lot of follow-up on that work. And as I said, with some controversy about the proper interpretation of these results. Since my time is up, let me conclude. We discussed a large class of continuum field theories which have this d-2 form global symmetry. And we consider it with a particular background field, where the background field has constant field strength for the background gauge field of the d-2 form global symmetry, which is a mouthful for something which is actually quite simple. And there was 2 special cases I studied. In fact, the 2 special cases are essentially the same. Dynamical U1 gauge fields with constant charge density. That was the first example. And the second, certain nonlinear sigma model with a term which is first order in time derivative. And the special case of that was the continuum Lagrangian over ferromagnet. And in all these cases, we found an Adler-Jaquib-like anomaly that explicitly breaks the U1 to the D translation symmetry to a discrete group. And furthermore, that discrete group is extended by the higher form symmetry. Thank you.
Thank you, Nati, for this wonderful talk. Are there questions?
About the analogy with the BJ anomaly, the standard BJ anomaly, Is there a way to reformulate this breaking of the symmetry at the quantum level in terms of an anomalous word identity?
Yes, there is a conserved current, a translation current, but it's not conserved.
And what is the term that breaks the...
It's F, the field
okay.
strength. In this case, it's the field strength. In the other case, it's the pullback of omega to space-time.
Oh, okay, thanks.
So so there's a conserved current. And as with standard ABJ, you can have another current which is conserved but not well defined. So there are two currents. There is a current that is well defined but not conserved, and there is another current which is not well defined but is conserved. Very much like for ABJ. The only novelty is that the current that we're talking about is not a current of a chiral symmetry, but a component of the energy momentum tensor.
So, I'm curious, like, what happens if you take the large volume limit but fixed charge? Because it seems to me that the parameter goes to 0, but the symmetry remains the same.
Right. So if you take V to infinity with large charge, the effect goes away because what we had was K over V. So the charge density goes to 0. In that limit, the effect goes away. So the effect is hidden. Another limit you could study is K going to infinity with V going to infinity, so that you have constant charge density. Then you have another effect where the symmetry is continuous, but the extension is still there. Part of the confusion in the literature is people took various limits, and in various limits, the phenomena are completely different. The way to get it straight is not to take any limit, to study the problem before we take any limit. Finite volume, finite K, everything is finite. Study this system, and then if you want, you can take limits.
Okay, thanks.
Any other questions? Okay, so let's thank Nati again.